Hi, this is the final project presentation for ECE6775 High-Level Digital Design Automation for Group T4A. My name's Aiden, joining me is Nita, Edmund, and Barry, and we're going to talk to you about our final project, accelerating post-quantum cryptography, specifically crystals Kyber, on FPGAs. To understand why Kyber is relevant, we need to understand the impact of quantum computers on the field of cryptography. The security of cryptographic algorithms are centered around computational problems that are NP hard for classical processors to solve. However, many of these problems, including those used by popular cryptographic algorithms like RSA and Diffie-Hellman, can be solved by advanced enough quantum computers in polynomial time, posing a widespread threat to digital security. While quantum computers aren't advanced enough yet to solve these problems, experts suspect it's only a matter of time. The National Institute of Standards and Technology has standardized these classical algorithms until 2030, but have already searched for new quantum-resistant algorithms to standardize for the foreseeable future. From those, Kyber was selected to be the primary asymmetric or public-private key algorithm, often used to establish symmetric keys for existing secure algorithms like AES.
Okay, so first we'll start with an overview of the Kyber algorithm. Kyber is based on the ideas of learning with errors, or LWE encryption. LWE encryption is based on the idea of essentially representing secret information as a set of equations with some errors, or in other words, hiding secret information by adding some amount of random noise. Kyber uses the ring of polynomials of degree n with integer coefficients modulo some prime q. By default, Kyber uses q equals 3329 and n being 256, although these values are tunable parameters. In order to generate a key pair, we use a 3x3 public matrix of polynomial elements A, given some random polynomial vector S as a private key. The public key T is then generated by performing A times S plus E for some small error term E. Recovering S from T is computationally hard due to the error term as well as the math being performed over a finite ring with modular reduction. Then we can encrypt a message M using a sequence of matrix multiplications and another random vector R to generate two encrypted vectors U being A transpose times R plus some error term E1, and V being T transpose times R plus some other error term E2, and then with the message M added on top. This has the added advantage of allowing multiple different encryptions of the exact same input message, which makes it difficult to analyze correspondence between messages. Decrypting using a secret key is also a secret series of vector operations. Simply, you do V minus U transpose times S, and as shown in the math to the bottom right of the screen, all the terms cancel out, and as the error terms are specifically chosen to be small, this allows the original message to be recovered.
Now we'll talk about some of the key components of the Kyber algorithm, which we identify through profiling the reference code. On the bottom of this slide, you can see a flame graph of the Kyber execution with 1,000 encryptions in a row. We've basically divided all the kernels in Kyber into three different parts. The first being random sampling. Kyber basically sampled noises to enhance the encryption using the shake algorithm. That takes about a quarter of the runtime. Then we have the entity and the inverse entity. They transform polynomials to and from the entity domain for fast modular computations. These take 30% of the runtime. And lastly, we have the Montgomery reduce and the Barrett reduces. These reduces multiply and reduce two polynomials in the entity domain and take up around 35% of the runtime.
The numbered theoretic transform, NTT, is a method used for efficient polynomial multiplication in modular arithmetic, a fundamental operation in cryptographic algorithms like Kyber. In Kyber, polynomial arithmetic is at the core of key generation, encryption, and decryption processes. The NTT operates by converting polynomials into the frequency domain, where multiplication becomes simpler. Once the multiplication is performed pointwise on the transform's coefficients, an inverse NTT, INNTT, is applied to bring the result back to the original domain. This transformation significantly reduces the computational complexity of polynomial multiplication, making it faster and more practical for cryptographic systems. Optimizing the NTT is crucial because it involves thousands of modular additions, multiplications, and reductions, making it one of the most computationally intensive steps in Kyber. These operations are repeated multiple times throughout the cryptographic processes, meaning that the NTT has a substantial impact on the total runtime. Furthermore, the sequential dependencies inherent in the NTT, where each stage depends on the output of the previous stage, limit the potential for parallelism, particularly on hardware architectures, like the FPGA we're trying to implement it on. Given that the NTT and INTT are repeated frequently in Kyber, optimizing these computations can significantly improve overall performance, reduce runtime, and enhance the efficiency of the system.
We have two different implementations on the FPGA. One of them is the full Kyber, and the other one is just the NTT. For the full Kyber, we put the entire algorithm onto the FPGA, and this helps us reduce latency between the host and the FPGA, and also allows us to speed up other parts of Kyber. The disadvantage of that, however, is that we're bottlenecked by the random number generation, which doesn't have a constant loop bound, and also we're bound by the resource utilization, so we can't optimize every kernel in Kyber. The other implementation with just the NTT allows us to put a super well optimized NTT onto the FPGA. We can have all of the resources dedicated just for the NTT, and it's also simpler to implement because we don't have to transform all of the original functions into HLS. The problem, however, is that we will be going back and forth between host and FPGA to complete the Kyber algorithm, and this also limits our speedup potential because NTT only takes about a third of the runtime.
To obtain concrete results, we pushed our two FPGA implementations through the high-level synthesis lab, the first having just the NTT algorithms in FPGA hardware, and the second having the entire algorithm in FPGA hardware. From these, we can obtain a comparison of their resource utilization and latencies. For the utilization, we can see that overall, having the entire algorithm in hardware has higher utilization than just the NTT algorithms, as we'd expect. However, there are a couple key takeaways. The first of these is that there is unusually high DSP usage overall compared to previous labs. This is due to the multiplication involved in Montgomery conversion, which is a key part of making performing arbitrary moduli fast in cryptography to achieve the necessary modular arithmetic. In Montgomery form, performing a modulus over one value can be converted to performing a modulus over an arbitrary other value. By picking this other value to be a power of 2, moduli and division in hardware can become fast. However, converting in and out of Montgomery form requires a multiplication step. This is also a key factor in why the overall algorithm can't be as optimized as one might hope. Specifically for NTT, we had to avoid unrolling a large loop iteration as there weren't enough multipliers. The second key point to notice is that the flip-flop utilization for the overall design hardware is actually less than just having the NTT algorithms in hardware. This is surprising, but becomes clear once we consider the optimizations present. When performing just the NTT algorithms, we can optimize more heavily, resulting in large flip-flop usage for unrolling and pipelining intermediate results. However, with the entire design, many fewer optimizations are present, allowing for flip-flops to be reused over many cycles, resulting in an overall lower flip-flop utilization. Finally, we can also take a look at the predicted latencies of each from synthesis. For the NTT algorithms, latency ranged from 2,610 when performing NTT to 4,378 when performing the inverse NTT due to an extra multiplication reduction at the end. However, for the entire design, the lowest latency was finite, not an expected order, about 500,000, but the largest latency wasn't known by the algorithm. When making this constant bound, it became astronomical. This is because the algorithm currently uses rejection sampling to achieve random numbers in a given modular ring, resulting in unknown latencies. In practice, the latency of the entire algorithm will therefore be close to the minimum. One other note is that, despite being a considerable 36.2% of the overall computation when roughly profiled in software, the NTT implementation alone took less time than hardware than it would be expected based on our hardware implementation, based on from the latency of the overall implementation. This is due to the fact that we can more aggressively optimize the NTT alone when more resources are available. In addition to getting predicted latencies from Vivado, we additionally put our hardware on the physical FPGA to gain experimental data for the time each implementation takes. Pure software, having the NTT algorithms in hardware, and having the full Kyber algorithm in hardware. Below, you can see that having the NTT algorithms in hardware resulted in some speedup over software, but was overall limited in the amount of speedup due to the fact that the majority of the Kyber algorithm was still in software. Putting the entire algorithm in hardware resulted in some speedup over software, but not as much as we ultimately hoped for. This is not only due to the fact that the ARM core is running at a higher frequency than the FPGA hardware, allowing it to perform more operations in a given time, but also that Kyber overall has many different types of operations, or kernels, it needs to do as part of the overall algorithm. With each operation or kernel requiring different hardware, it can be difficult to reuse hardware across the entire application, resulting in fewer available resources and less ability to replicate hardware to achieve parallelism. Here, we wanted to give a quick demonstration of our Kyber implementation running on the actual FPGA hardware. You can see that I'm currently logged into the FPGA. On the left, you can see our main hardware module. We focused on implementing encryption. Accordingly, this module takes in a public key from the input stream and uses it along with randomness to generate a shared secret as well as ciphertext. The idea is that a recipient could use an associated private key to turn the ciphertext into the same shared secret, which could then be used as keys for later symmetric encryption. On the right, we have our software test bench that tests our pure software implementation. This is an adapted version of the upstream Kyber implementations test bench. Specifically, here we generate 20 public-private key pairs, where here reps is 20, measure the amount of time it takes to generate ciphertext for all of them, and then verify that the decrypted shared secret is the same as the generated one. We can see, along with previous test bench output, that this takes about 120 milliseconds on the FPGA. Our FPGA implementation does the exact same thing, except now the design is in hardware, so encryption is turned into reading and writing all of the hardware input and output streams. We first send all of the inputs, then read all the outputs to amortize communication latency. Here we can see that the latency in the execution time is drastically lowered. Now we're only at around 83 milliseconds.
Okay, next we'll talk about some rooms for improvement. Currently, the main bottleneck in our algorithms is the random number generator for the polynomial matrices. Ideally, we want a deterministic random number generator that is both parallelizable as well as very fast. This is because in order to generate values in our polynomial ring, we need uniform coefficients under 3,329, which requires rejection sampling, which can take an indeterminate amount of time. As for our other kernels, currently most kernels are fairly well balanced in latency, so there isn't one big target for optimization, and instead it would be more important to perform a bunch of small optimizations across the board to lower all the latencies of the kernels. And you can see in the bottom right that they're mostly evenly distributed, and all of these are much smaller currently than the random number generation is taking.
In this project, we focused on FPGA acceleration of Crystal's Kyber, a quantum-resistant cryptography algorithm driven by the growing threat quantum computing poses to traditional cryptography. We implemented and evaluated 2 FPGA designs, a full Kyber implementation and an NTT-only implementation. In the process, we made the entire Kyber algorithm synthesizable, verified its correctness on an FPGA board, and developed FPGA host software to generate and test bit streams for both designs. The NTT-only implementation was specifically optimized, achieving up to 75% speedup in latency, albeit with increased resource utilization. Overall, we integrated a cohesive design, conducted co-simulations, and performed profiling to uncover opportunities for further optimization. As we continue exploring future advancements, we are excited about the potential for further improving performance and efficiency with Kyber. Thank you for listening.